Good afternoon, everyone. Firstly, thanks to all our attendees for joining us for this exciting free webinar. For the next 1 hour, get ready to delve into the modern world of multiphysics modeling. My name is Manpreet Kaur, and I will be moderating this exciting live webinar titled Modeling Hydrogen Fuel Cells and Electrolyzers. Not wasting any more time, I take this opportunity to introduce our esteemed speaker, Dr. Lekhraj Malviya, who is the technology specialist in COMSOL. To give a brief introduction, Dr. Lekhraj Malviya is a technology specialist at COMSOL, specializing in electrochemistry, chemical, and CFD. He received his Ph.D. from IIT Roorkee, his master's degree in chemical process design from Maulana Azad National Institute of Technology, Bhopal, and his bachelor's degree in chemical engineering from Ujjain Engineering College. Prior to joining COMSOL, he worked as an assistant professor for 4 years at JECRC University, Jaipur. During this webinar, requesting everyone to share their questions by writing in the chat box. Also, we will be conducting polls during this 1 hour webinar, so don't forget to share your opinions. We will be providing the information about the presentation on demand after the webinar. You can share your interest to us by writing at info@theworldpost.com. Subject: Presentation information of COMSOL webinar. And now allow me to welcome our esteemed speaker, Dr. Lekhraj Malviya, who will be starting the presentation and also sharing live demonstration during this 1 hour webinar. Dr. Malviya, requesting you to share your screen and start the presentation.
Yeah, thank you, Manpreet, for giving me this kind of introduction. And I hope my screen is visible to you all. Please confirm.
Yes, your screen is visible.
So, good afternoon, everyone. I am Lekhraj Malviya, an application engineer for electrochemistry at COMSOL Multiphysics. So, thank you for joining me today. We are starting with the one big picture. So, for many years, we have relied on traditional energy harvesting tool and like burning coal, petrol, or diesel to power our world. So, however, these sources are limited and they have caused the serious pollution and the global warming as well. So, today things are changing fast, and we see electric vehicles on the road and more use of the solar panels and wind turbines, and a strong push for the cleaner and renewable energy. So, as a humans, we always look for a better way. And now we are asking what clean energy source can power the future. So the powerful answer is hydrogen. So hydrogen is a clean and efficient and only the produce water when used. With the electrolysis, we can produce it from the water using the renewable electricity. So countries like Japan, Germany, South Korea, Australia, and many are already using their hydrogen in a vehicle and for the power generation. But designing hydrogen systems like fuel cells or electrolyzer is a little bit complex. They involve gas flow, heat transfer, chemical reactions, and electricity, and all working together. This is where COMSOL Multiphysics helps. So COMSOL lets you model everything in a one place, just like flow, heat, electrochemistry, and structure as well. So you can test design virtually and improve performance of your fuel cell and electrolyzers and reduce the cost as well. So today I will show you how we use COMSOL to simulate and optimize hydrogen fuel cell and electrolyzers from the geometry to efficiency. So before we dive in, I would like to launch a quick poll to better understanding our audience today. So you will see a question on your screen. So please take a moment to respond. This will help me to tailor the session better based on your background and expectations. So I will give everyone a few seconds to submit their response. Yeah. So I can see 41% of more of the people are new to the COMSOL multiphysics simulations, and 14% are regular user of the simulations tool. So thank you for this information. So accordingly, we can tailor our session. So now we are starting. from the product to the final use of the hydrogen first. So hydrogen goes through several key stages, and each stage simulation with the COMSOL multiphysics play a vital role in making system safer, more efficient, and the cost efficient. So first we are talking about the hydrogen production. So electrolysis is the main method to using electricity to split water into the hydrogen and oxygen. So with the COMSOL we can optimize temperature, pressure, and voltage, and maybe simulate gas bubble formation from the electrolyzer and study membrane degradation, so helping this improvement of the performance, the durability of the electrolyzers can be done by COMSOL. So next is the hydrogen storage and the transportation thing. So hydrogen is stored in high pressure tanks or underground caverns, and within the metal hydrates also, and transport via pipeline or trucks or ships. So COMSOL help to simulate thermal effect during the fast filling, and predict the material stress, assess the leakage risk, and the model pressure and temperature variation over the distance. So ensuring the safety and the efficiency during the storage and the transport. So finally, we are coming to the hydrogen utilization. So fuel cells is converted hydrogen back into the electricity for the vehicles or industrial systems. So hydrogen enable us to optimize fuel cell geometry, and manage heat and reaction zones, and predict the long-term performance. So in short, COMSOL allow us to virtually explore and improve every setup, every step of the hydrogen value chain. So this is the different type of the fuel cells and the electrolyzer are used in the different situation, and each comes with its own engineering challenges. So there where multiphysics simulations become essential. So for the example of the proton exchange membrane fuel cell, they are widely used in the vehicle and operated at a low temperature, but require precise control over the flow and the water flow and the heat to avoiding flooding and the drying for the membrane. So in contrast of the solid oxide fuel cells, they are working at the high temperatures for the stationary power. Here we need to handle thermal stress and gas transport, and also the material degradation. So on the electrolyzer side, so PEM and alkaline electrolyzers are used to produce clean hydrogen. So they must minimize the energy losses and prevent issues like shunt currents, especially under the dynamic conditions. So no matter the system, we are dealing with the complex interaction of the physics, that is the fluid flow, heat transfer, electrochemistry, or gas diffusion, and even the structural mechanics also. So with the COMSOL multiphysics, we simulate all of these interaction together in a one unified environment, which is helping us to design better system, catch failures early, and reduce the prototyping time and the cost as well. So now that we have seen the range of the technologies, let's move into how we model this system step by step in the COMSOL. So for truly understanding the optimized hydrogen technologies, we need to look at the full picture, from the macroscopic reaction happening inside the membrane to the overall behavior of an entire fuel cell or the electrolyzer stage. So this is where the COMSOL multiphysics stand out, and it allows us to model across different length scales, all within the single simulation environment. So first we are talking about the unit cell scale, and at this level we zoomed into the electrochemical core of the system, and here simulation help us to analyze the ion transport, gas liquid reactions, and species diffusion, and multiphysics flow and heat generation also. So we can visualize how each layer, that catalyst membrane, diffusion layer, perform under the various conditions. When we talk about the bipolar scale, so now we look at the flow field design. This is where the optimize the gas distribution channels, and pressure drops due to its bending pipe. Flow is uniform or non-uniform, so flow uniformity also we can see that. So a good design here, the assurance the uniform current density and avoid the flooding or the dry spot. When we talk about the stake level, so this level is the very highest level. So we can simulate the performance of the full fuel cell and electrolyzer stake. So since modeling every detail at this level is computationally little bit expensive, and COMSOL use the smart technologies like homogenization and porous media approximation. So this let us study the current distribution, the heat and water management, shunt current, and thermal stresses for the stack scale. So by linking these scales together, COMSOL provides both fine detail and the big picture insight, letting us to improve component performance without losing sight of the system level behavior. So this multi-scale approach is essential for the accelerating the design, reducing trial and error, and ensuring the hydrogen technologies perform reliability in the real world. So far, we explored how simulation connects different modeling scale from the micro to macro. So now let's take the understanding up and apply it in the to the real world challenge in the hydrogen system design, which is called the shunt current in the alkaline electrolyzer stakes. So before we starting in the real world simulation example, I would like to launch another quick poll to better understand your specific interest. So this time I want to know where you are focusing your fuel modeling effort. So are you working on automotive applications like fuel cell or electric vehicles, or perhaps you are targeting stationary or the power grid systems where fuel cells are used for the backup and distributed power? So please select all the type, and if you are your use case isn't in the list, so feel free to share it in the chat also. So your answers will help me to tailor the remaining part of the session to what matter most of you. So please participate in that poll question. Yeah. So yeah, most of the persons are gave the answer, and most of people are using the automotive application. It is the 53% of our audience, and 20 to 23% is the stationary and the power grid applications. So yeah. So by one, we are taking care of these things. So first of all, we are see how shunt current affect that electrolyzers stakes. So we will talk about this thing, and after that, some scaling parameters and the stack level fuel cells we also see. So this is our shunt alkaline electrolyzer stakes. So let's look at a common bottleneck in the industrial hydrogen production, that is called the shunt currents in the alkaline electrolyzer stakes. So alkaline stakes, which is generally found in the fertilizer plants, green steel lines, and hydrogen refueling station. So combine many cells that share the same potassium hydroxide electrolyte. That share the pathway makes the construction straightforward, but it's also lets unwanted current bypassing that intended electrochemical routes. So this parasitic current cut the efficiency of this electrolyzers and contaminate the hydrogen also, and pose the safety risk, especially at high current and the temperature. So COMSOL multiphysics fix that visibility gap. In the one model we can build full 3D 20 cells geometry. So there is a 20 cells in the here. So couple ion and the electron transport, gas liquid flow, and heat and electrochemistry also. So we can multiphysics together in the COMSOL multiphysics and pinpoint exact where the shunt current emerge and why. So we can see with the help of the COMSOL multiphysics. So virtually test manifold shapes and isolation layers and the operating conditions before the hardware exists. So the outcome is very clear. We need to the pure hydrogen, and we need to higher energy efficiency, and we need also the safer operation and the shorter development cycle. So next we will walk you through how we set up that simulation from the geometry to results. So Here is the full 3D geometry of our alkaline electrolyzer stack. So it's a sequence of the identical unit cells stretching in the x direction. So we can see every layer, cathode, anode surfaces, and separator plates in between, and bipolar plates is also there, and the inlet and outlet manifolds that carry the shared potassium hydroxide electrolytes. So geometry is the critical because we dedicated to three fundamentals: how ionic and the electronic current flow, the way of the hydrogen and oxygen gases leave each cells, and where the heat accumulated under the load. So with the help of the COMSOL, we can capture all of this in one model. So we can predict the hot spot where the overheating might occur, detect the non-uniform current densities across the cell, and locate where the shunt current might form. So by the building a precise and the realistic geometry, we are able to simulate actual behavior. So now that the geometry is in the place, let's look the results. That is the current distribution kind of things, and temperature maps, and exactly where those shunt current appear, and how design trick eliminate them. So now we are set up the geometry, and next step is to look inside the stack that the electrical behavior happen during the operation. So in the COMSOL, we model two main potential. One is the electrode phase potential, and another one is the electrolyte phase potential. So electrode phase potential, which derive the electrochemical reaction, and electrolyte potential, which tells us about how ions move through the liquid. So by simulating both, we get a full map of where the reaction are happening and how efficiency the current flow. So ideally, we want to the uniform voltage gradient across all cells, but in the practice, some areas resist currents. These high resistance zone can lead to be uneven reaction rates, and localize the overheating and reducing energy efficiency also. So with the COMSOL, we can pinpoint this weak hot spot and redesign the compounds like electrodes and separators to balance the current and the enhance durability. So this electrochemical modeling step gives us deep insight into the real behavior inside that step, and set the stage to study one of the most critical byproduct of the voltage imbalance, that is called the shunt current. So with the electrode and the electrolyte phase potential mapped, we can now focus on the major performance issue in the alkaline electrolyzer, that is called the shunt currents. So these are the unwanted parasitic currents that flow through the shared electrolytes and manifolds and bypassing the indented electrochemical path. So in COMSOL, we simulate how stack geometry, electrolyte conductivity, and manifold flow distribution influence where this shunt current forms. So these results often show that the lower manifold in the channel and for more prone to these losses, where the voltage gradients and the flow paths overlap most aggressively. So by adjusting to design parameter in the simulation, we can predict that and visualize exactly where these losses occur. So well before the physical testing. So this is enable to engineers to redesign the manifolds, add the insulation barrier, and mitigate the unwanted current loops. So ultimately, this improve the hydrogen purity, boost the efficiency, and enhance the stack reliability. So now that we understand where the shunt currents form, let's explore how they affect the overall performance of the system. So to evaluate the performance of our electrolyzer stack, we focus on three key metrics. One is the shunt current. So shunt current, we track this across each cell operating at the 1.8 volts, and the highest shunt currents appear in the lower manifold channels, which is driven by the strong voltage gradients and uneven electrolyte conductivity. So, and if we are talking about the Coulombic efficiency, this is lower at the low stack currents, and where the shunt current losses form the larger percentage of the total current. So as we increase the stacks current, so Coulombic efficiency rise sharply, meaning more current goes toward the actual hydrogen production. Then we switch to the energy efficiency. So it is starting low due to early shunt current, and the polarization losses peak around the 1300 amperes, where the system operating optimally, and then drops again at the high currents due to the ohmic and the activation losses. So this performance curve give us a clear optimal operating window, and where efficiency, reliability, and the cost are balanced. So while alkaline systems offer a proven performance, we can go further. So to explore higher efficiency and the integrated thermal operation, let's shift focus to the solid oxide electrolyzer cells or SOECs. So solid oxide electrolyzer cells or SOEC are emerging as a powerful option for the industrial scale hydrogen production, especially where the waste heat is available. So it is operating condition at around 800 degrees centigrade, and SOEC used high temperature steam electrolysis to the reduce electricity demand. So this makes them highly efficient when the integrated with the heat source like refineries, chemical plants, and the renewable CHP systems. So there is the ceramic electrolytes move the oxygen ions, not protons, which means we can co-electrolyze steam and the CO2 to make syngas. So opening doors to the synthetic fuels and chemicals, not just for the hydrogen. But these benefits come with the challenges. So thermal stresses material degradation and complex gas flow is also occurred. So COMSOL Multiphysics tackle all this in the one coupled model. We can map this thermal gradient and the manage stresses, refine cell geometry to uniform the current densities, predict long-term degradation and the flake failure risk early, just like before a single part is built. So next, let's see how we construct these multiphysics models, starting the unit cell scales. So this is the unit cell model. We are explicitly define our anode, cathode, and solid oxide electrolyte layers. So here we are using the ceramic membranes. So using COMSOL multiphysics, we apply detailed the boundary conditions, temperature dependent material properties, and fully coupled physics to simulate that ion conduction through the electrolyzers, electrolytes, gas diffusion in the porous electrode, electrochemical reaction at the interface. So this detailed setup let's capture key outputs like local potential gradients, temperature fields, and gas species distribution. So with this information, we can identify the hot spot, non-uniform current densities regions, and area prone to the degradation. So this critical insight for the optimizing the SOEC performance and the durability. So once this unit cell is the models, we scale to the system level. So for the tracking gas flow and velocity and species transport under the real operating conditions. So next we will see how velocity and the gas composition profile highlights the performance trends to across the cell. So using the COMSOL, we map the velocity magnitude distribution within the SOEC cell, and that results show lower velocity in the three parallel flow channel and compared to the inlet and outlet, which exhibits a similar velocity magnitude due to equimolar nature of the gas flow. So next we track the molar fraction of the hydrogen and the steam. This is the H2O in the gas format, and the byproducts along the same path. And this reveal how composition shift as the gas reacts and migrate, and how those shifts influence the local current density. So at different feed condition like varying the steam axis or the hydrogen utilization, we observe the strong interaction between the reactant availability and partial pressure gradients and reaction zones. So these insights critical optimizing gas feed ratios, which is preventing the performance losses and ensuring the high efficiency under the realistic operating conditions. So now let's examine how changes in the gas composition, particularly hydrogen concentration, which can be directly affect the reaction rates and overall cell performance also. So here is the simulation results show that higher hydrogen molar fraction near the outlet leads to the drop in hydrogen partial pressure, causing the decline in the local current density. So with this non-uniformity of the gas composition in the electrochemical activity can lead to the performance degradation, uneven thermal and the material aging, and lower overall efficiency. So to mitigate these effects, we both cell design and system level control must be optimized by the adjusting flow field geometry diffusion layer properties, and the reactant stoichiometry to maintain the uniform operation. So this underscores the power of the detailed multiphysics simulation in the COMSOL, enabling to better design decisions and improving long-term durability to efficiency of the SOEC. So next we will examine how gas composition shifts to also influence the thermophysical property and why accurate modeling of this effect is critical. So in high temperature system like SOEC gas property like density and viscosity, so changes significantly as hydrogen and the steam ratio evolves along the flow path, and this shifts the effect of the flow velocity and pressure drop also, and species transport inside the porous electrodes and overall fuel delivery and the reaction efficiency. So if we ignore these effects, we risk underestimate the fueling starvation, local pressure, and build up or transport limitation. So with the help of the COMSOL multiphysics, the gas property are dynamically linked to real-time composition and making the model more accurate and the predictive. So having this explore hydrogen production with the SOEC. So let's now shift focus to the hydrogen utilization, which is starting from the PEM fuel cell performance under the dynamic and the non-isothermal condition. So this is our third type. So first type we see only the electrochemical part. In the second, flow was included. Now we are doing the multiphysics modeling. With the electrochemistry, fluid flow was there, and heat transfer is also included in the non-isothermal PMC. So imagine this fuel cell car is driving into the hot summer day, and when the driver presses the accelerator, the car needs more power. So the fuel cell has to work harder, which means it make more heat and more water inside. So the heart of the fuel cell is a thin membrane that conducts the hydrogen ions, but this membrane is very sensitive. If it gets too dry, it can't move ion easily, and the power drops. And if it's too wet, so water can be block the flow of gases and the reaction slow down. So keeping the right balance of the water and heat is very important. That's why we use the COMSOL multiphysics simulation that includes the heat transfer to see how the cell heats up, and water movement, including the water being pulled by the ions, that is the electroosmotic drag. Another one is the back diffusion, which is the water moving back to the balance of the sides, and water leaking through the membrane, that is called the permeation. So these coupled effects show how temperature and humidity evolve during the load changes and how they affect the reaction zone. So with this insight, we can optimize the humidification strategies and improve the thermal controls, and again design the PEM fuel cell that stay efficient even in the real world driving conditions. So now let's explore how we build this detailed multiphysics model in the COMSOL. So again we create the understand the PEM fuel cell in the detail. We model the every critical layer in a one COMSOL model. This is the membrane electrolyte assembly, that is called the MEA, where the electrochemical reactions occur. Another one is the cathode GDL and anode GDL. It is the gas diffusion layer to move gases in and liquid water out. Flow channels, which is the distributed reaction uniformly, and cooling channels to remove excess heat under the load changes. So all these parts interact, so we use the fully coupled multiphysics approach, which is the including the heat transfer, gas and water transport, and electroosmotic drag also. So this unified model predicts the power output that map the temperature and humidity inside the cell and show how those conditions affect the proton conductivity and the overall efficiency. So with these results, engineers can fine-tune the material, layer thickness and the channel geometry, which is responsible for the designing PEM fuel cells, and that run cooler and stay hydrated and last longer also. So now that the complete cell is modeled, let's examine the key electric behaviors, specifically how voltage varies across the different layer and what that means for the performance. So when we look at the simulations results, we see the most of the voltage drop happen in the gas diffusion layer or GDL. So while these layer are the essential for the letting gas in and pushing water out, they also add some electric resistance, and this resistance cause ohmic losses, which means the cell loses some energies as heat instead of the useful power. So understanding the where these potential drop across the these potential drops occur help us to find a way to reduce the losses and the improve that fuel cell overall efficiency. So beside these electric losses, the heat built up inside the fuel cell, which is play the important role in its performance and the durability. So let's see what the model reveals about the temperature distribution. So this is the temperature distribution for the PEM fuel cell, and the biggest temperature is raise happen in the membrane electrode assembly or the MEA. So our simulation shows that MEA can get over the 10 degree hotter, 10 degrees centigrade hotter than the coolant entering the system, and these heats come from the electrochemical reactions and resistance to the current flow, especially when the cells is working very hard. If we don't manage this heat well, so it can be dry out our membrane and damage it. So this cause uneven current flow and making the fuel cell wear out faster. So by studying both the electric and thermal details, the model helps us to design the better cooling path, choose the material wisely, and building the more reliable fuel cell. So now that we understand the temperature effects, let's look at how water inside the fuel cells impact its performance. So the gas flow through the fuel cells and relative humidity rise near the outlet because water is produced during the reaction. So this extra moisture makes the membrane more conductive, which helps increase the current density in that area. So understanding this, this is the key for the designing humidification system and the flow fields layout. So by knowing how water builds up inside the cell, engineer can adjust the gas flow, or we can modify the channel design as well, or the operating condition to keep the fuel cell working efficiently to avoid the problem like the flooding or the drying out. So far we have the focus on the single cell PEM fuel cell, but in the real application, cells are stacked together to deliver higher power, which brings new challenges, especially with the temperature and the water management across the whole stacks. So this is our fuel cell stacks. So when multiple PEM fuel cells are stacked to keeping each cells at the similar temperature, it is very important. And if some cells run cooler or hotter, water vapor condenses unevenly, causing the performance difference that lower the stack efficiency and the reliability. So cooler cells can be flooded with the water, blocking the oxygen needed for the reactions, while hotter cells may be dry out and damaging the membrane over the time. So these problems shorten the fuel cell stack's lifespan. So to address this, we use the COMSOL Multiphysics to model a detailed 5-stack cell, including the heat generation and water movement or gas movement, and also the cooling flow for the and electrochemical reaction also. So we tested different flow designs like a straight, serpentine, and bio-inspired pattern, and I have one user story for the same thing, and the results show that which layout spread heat evenly and the improve water management. So this lets engineer pick better cooling and flow design early on the saving and time and cost also. So good thermal management powered by the simulation is the key to making fuel cell stacks efficiently and durability also. So now that we have seen the importance of the temperature and water balance in the fuel cell stack, and let's look at how we model this complex interaction in the COMSOL. So before starting our demo, we showcase some results also, how actually what happened inside that fuel cell stack cell. So this is the model which is representing the 5 cells PEM fuel cell stack, and each cell is separated by the bipolar plates that also the serve as a channels for liquid cooling. So inside the COMSOL, we simulate the several key processes all at the once, and this includes the temperature changes inside the stack and electrochemical potential in both the electrodes and electrolytes, and mass transport of gas like hydrogen, oxygen, and water vapor or steam, can say, and in each compartment, and the fluid flow and pressure also in the both gas and the cooling channels. So the COMSOL Model builder make this workflow smooth. It bring together and with the geometry setup, physical definition, meshing, solving, visualizing the results in the one place. So this multi-physics approach help us to better understanding how different parts of the stack interact, so we can make a better design decision and build more efficient and longer lasting system. So this is our COMSOL look like. So give me permission to share my screen again. So this is our COMSOL GUI look like. So when we started our COMSOL multiphysics GUI, let's so here we can see the example of the stack cooling PEM fuel cell. So in the geometrical parameter, so we can put our all parameter here, and we can use same thing in the geometry section. So if your geometry is this geometry is built in the COMSOL itself. If you want to import your geometry from the any CAD software, so we can directly import your geometry from the other CAD tool. So I will showcase you. So our COMSOL when it's launching, so our GUIs look like the same, and either you can go with the model wizard or the blank model. So generally we select the model wizard. So in the model wizard, which kind of fuel cell or which kind of modeling you want to do. So from the 3D to 0D we can choose. So as of now I choose the 3D, and in the 3D in for the PEM fuel cell, I want to use fluid flow, the multi-phase flow. In the multi-phase flow, I have two-phase flow in the phase field. I choose the phase field here. So this is the laminar flow, and I want to heat also. So I choose the heat transfer from the non-isothermal flow, and my model will be ready. So after model means physics selected, we are going to the select the study. Is your study is time dependent or stationary you want. So I just choose the time dependent study with the phase field initialization, and after that we just click on the done. So with the help of this our initial GUIs look like this thing. So in the initial your parameter estimation is not there, and if you want to do some either you can directly import from the any CAD, so any imported file, or we have different kind of the model we can directly import from the other CAD tools. After the model import, or you can build in the geometry. After the building the geometry, we have to assign our material. So in the material we have COMSOL having the dedicated library. You can use directly choosing from the battery, electrolyzer, electrodes kind of things, or dedicatedly fuel cell library is also available. So in the fuel cell, aqueous, alkali, molten carbonates, polymer electrolytes, and solid oxide is also available. So we can choose the directly material from the material library. As of now we are choosing the steel as the outer body, and water liquid inside the our membrane, and one is the water equilibrium. So material we can choose. After the material choosing, we just select the our physics. One of the physics we are using the hydrogen fuel cell, so which is allowed the electrode phase. So which kind of the electrolyte here it is. So from the zoom we can see we are choosing the stacks, and you can see clearly here. And for the edit anything, so is your electrolyte conductivity from the material. So whatever you choosing the material and you assign it, so it is directly coming from the material, or you can change it by the user define also. So we can choose from the material. After that electric conductivity phase, and which kind of the hydrogen phase, H2 is where, and oxygen we can assign in the physics term. So this is called the graphics window. This is our in the middle is the setting window, and this is our model tree builder. So after the setting up hydrogen fuel cell as a physics, we are look like just pressure only. So for the pressure, we have to solve the Darcy's law in the, because our membrane is the porous. That's why we are choosing the porous medium. So I have to select the porous media. Where is the fluid? Where is our membrane? So we can choose directly by the Darcy's law. And I need to see a heat effect also, and heat effect is the porous media. So we have dedicatedly physics to solve in the porous media, and which equation is solving by the COMSOL. So we can see directly by the equation. So here is our equation for the hydrogen fuel cell, which kind of equation we have to solve. And similarly for the Darcy's law, we can see which kind of equation we have. So this is the part of the physics. In the heat transfer, again we can see our equation, which kind of equation, energy equation solving in the heat transfer in the porous media. For the porous media, we have dedicatedly one node which is allowed to you select the where is your porous media, we have to assign it. And we can see the name. This is our membrane, GDL, and end blocks. This is in the end. So after the setting up this geometry, material, the physics, we have to select this multiphysics nodes. So in the multiphysics, which equation we are solving together. So first off, we can see here the coupled interface. One is the electrochemical solved together with the heat transfer. So we have to select the electrochemical physics, and here is the heat transfer. So with the coupling of both, either it will be in one-way coupling or two-way coupling, we can do the same thing. And in the geometry parameter, I just showcased to you in earlier. So we can in the setting, we can see in the parametric study also. So in the parametric study, we can solve the parametric strip. So this is allows to you which kind of parameter you want to strip. Suppose if our unit cell thickness, so if this unit cell thickness is suppose this is the n number of cells, there is 5. So we need to change the number of cells to the 5. So we just type here, so n cell is number of cells. So I want to check from 1 to 5. So COMSOL itself give the result for the ones number of cell 1, sec 2, 3 to 5. So we have to define here that thing. So this is called the parametric strip. And mesh count is also important and crucial role in the any software. So COMSOL tell you about the user control mesh and the physics control mesh. If you select the physics control mesh, the COMSOL taken care of the all physics based controlled mesh. So we can do the mesh. After the meshing, we switch on the study. In the study, first study is for the current distribution. So here we are doing the stationary solving, and we do not go to the solver settings. We just jump to the result. So post processing itself happening in the our COMSOL itself. So we can see here the electric potential with respect to the ground. So it is showing that which kind of electrode potential coming through the lower to higher. Electric potential, we can see mass friction. Also we can see by the streamlines, whichever we have seen in our PPT. So this is the hydrogen, how hydrogen is coming through the inlet to the outlet. And this is the oxygen's, this graph is for the oxygen. So oxygen mole fraction, it is showing that. So from the inlet to the outlet is showing. And water activity in the hydrogen, we can also see in the post processing results. Temperature is the very crucial play crucial role in it. So we can see which kind of temperature and in every and each stake cells. So it is starting from here to here, from inlet to outlet. We can see which kind of temperature we are getting. And in the cooling channel, what is the status of the temperature? So we can see in the post processing itself. So for the fuel stack modeling, this is the very big advantage. We can see easily, including the complex feature like the porous electrode, gas diffusion layers, and cooling channels. We also couple the multiphysics like heat transfer, electrochemical reaction, and gas transport and fluid flow also within the same model. So the platform support the parametric study too. I told you earlier this like the like a flow rate, channel size, or material properties without the rebuilding the model from the scratch. So and once the simulation runs, so this is the part of the post processing tool allows to create clear visualization like temperature maps, current density plots, or flow streamline that reveals the what's working and what needs to improvement. So this is kind of the flexible all in the one workflows which saves the time, reduce the need for the physical trials, and speed up the innovations. So please. Yeah, so one of the biggest advantage of the simulation is the being able to test and the refine design virtually, so without having the build multiple physics prototype. For example, imagine an automotive company trying to reduce the weight of the this fuel cell systems, but without the losing their thermal performance instead of the manufacturer, and the several version of the cooling plate also. So they use the COMSOL to simulate different geometry and the flow paths to saving both time and the cost. So in the electrolyzer development, researchers have also used the COMSOL to explore how membrane thickness and electrode structure affect the gas crossover and the efficiency. And this kind of the insight helps guide material choice before the anything is built. And simulation isn't just about the design, it's also about the durability. We can virtually test how system respond to rapid cycle, start and stop conditions, and or stream loads, helping which is engineer case the reliability issue early. And this kind of the virtual prototype is shorten the development cycle, improves the product reliability, and accelerate the innovations. So now that we have seen how simulation help us the optimizing individual fuel cells and stacks, so let's look at how this approach is accelerating innovation at the industry level. And we have one of the user story I told you before, which is from the auto industry, because our many persons is interested into the auto industry. So here how Toyota is using the simulation driven design to rethink fuel cell technology together. So let's take the real world example that show the true power of the simulation, and this is comes from the Toyota. So in the most of the traditional PEM fuel cell, gases are distributed through the straight or serpentine channels, and these are easy to manufacture, but they comes with a serious trade-off. Like they can use uneven gas flow, water accumulation, and higher pressure losses, with the ultimately hurt the fuel cell performance. So Toyota engineers take the advantage of the COMSOL multiphysics, and they rethink this to on the design mode method that is called the generative design. And this method inspired by the nature, when thinking about the branching patterns of the leaves and lungs or blood vessels, and means they are mimic the nature's kind of inspirational structure. So these systems that evolved to distributed fluid efficiency. So using this nature inspired approach, Toyota generated 4 new kind of flow field design, which is the microchannel optimized for even gas distribution and better water removal, and also the lower pressure drops. So and this the result were impressive. So these new designs outperformed conventionally one in the simulation, showing improvements in the reactor distribution and power output also even better. So when they built a real prototype and tested them, the experiment results mesh with the simulations and a perfect validation. So this case highlight a key message: simulation doesn't just help us tweak what already exists; it's enable to true innovation also. And we can make with the help of the simulations like COMSOL design a better, smarter, and system from the scratch itself. So with the COMSOL, company like Toyota can move quickly from the bold ideas to the working products, and cutting the development time and improvement the performance and staying ahead in the hydrogen race. So this is our last poll questions as we are approaching towards the end. So everybody can please take it. I request to everyone, please, a part of that, you can participate in the poll question, please. Yeah, thank you. Many of the 53% audience I try out the COMSOL for his project or her project. So today we are explored how simulations bridges the between the gap. Uh, wait a second. Yeah. So today we explored how simulation bridges the gap between the concept and the reality in the hydrogen energy systems, from the understanding the electrochemical behavior inside the SOEC and PEM fuel cells to visualizing a complex interaction like heat, humidity, and the gas flow. So COMSOL empowers us to make informed design choice early. As we look to the cleaner and hydrogen powered future, the simulation isn't just a tool, it's a catalyst. It helps to engineers and researchers and innovators accelerate the development and reduce the cost and unlock the smarter and more reliable solution for the real world challenges. So thank you for joining me on this journey through the modeling and the innovations. So yeah, I open for the question. Yeah.
Thank you very much, Dr. Malviya. I hope you enjoyed this amazing presentations during the webinar and
Yes.
take back home a lot of needed information regarding the subject of the webinar. Now I open the floor for Q&A for our attendees. So our first question is from Mr. Keshav Kumar. I am looking at hydrogen as a chemical battery, as an alternative to ion batteries and kinetic batteries, gravitational batteries, where energy generated by renewable sources is used by hydrogen generation by the electrolysis process.
Okay, so this is, I thought it is a generic thing. We can use many kind of batteries. So hopefully I didn't understand which kind of question they want to ask. So it is better if you can write on our COMSOL support portal, so we can look into that.
So our next question is from Mr. Singh. Do we have a case study available for Toyota Mirai fuel cell study?
So Toyota Mirai fuel cell study we have, but due to the time constraint, we cannot showcase to you. But you can obviously visit our COMSOL website and asking for the user story at the learning center, so you can get many more study over the fuel cell and the electrolyzers. So it is helpful for you also if you want to do some fuel cell study. So many, apart from the Toyota, many studies or user story over there on the learning center itself. So yeah, this is the answer for this.
So there's a question by Mr. Singh again. Can you share with us the link to get the case studies?
Yeah, sure. So you have to write us on the support at comsol.com. So any query you just mention about this webinar you are attending, and you have that query. So definitely I will share with you.
So here comes the third question.
Yeah.
How can degradation mechanisms, for example, membrane thinning or catalyst decay, be included in long-term PEMFC modeling?
Okay, so for PEM modeling, for the membrane thinning and the catalyst decay, just I showcase to you. If we need to control over the fluid flow and the moisture also inside the PEM fuel cell, so we can, if you know, in the PEM fuel cell inside the membrane, if water is flooded, so our membrane cannot be exchange that ions. So its result is that our matlab, in fuel cell efficiency will be reduced in that case. So again, this answer is we have to more control over the heat exchange and also the water exchange, also the fluid flow. Yeah.
So the next question is, what are the key differences in setting up a PEM electrolyzer model compared to a PEM fuel cell?
So electrolyzers and the fuel cell, which is the basic difference. In the fuel cell, we are given as a uh, hydrogen as a fuel and get the electricity from it with the help of the fuel cells, and many types of fuel cells are available. And for the electrolyzer, we are producing the hydrogen. We are giving the electricity and producing the hydrogen. So as I showcased to you example of the SOEC, so where is the heat source is available, so we give the heat source as a electricity, not just for the hydrogen. We can generate the electricity from there. Means it is just vice versa. Means alternate things. So fuel in the fuel cell, you are giving the hydrogen as a fuel, and in the electrolyzer, you are giving the energy and or electricity, and you can get the hydrogen from the electrolyzers.
So the next question is from Mr. Arjun. In your point of view, what will be the future for hydrogen power in India?
Hydrogen power in India is expanding now. As a OEM of the COMSOL, we have many cases, so we are working on the things. So many people are working on the fuel cells, many of the electrolyzers. So that means in India, in the next 5 years, and you can see all our electric vehicles are there. Electric vehicle means car and bikes also, and nowadays I can see the buses also. So in the 5 years and upcoming 5 years, it's maybe possibilities we have some buses or some transportation vehicle over the hydrogen fuel cells.
So the next question is from Mr. Singh. Can we model hydrogen diffusion in the materials through COMSOL?
Yeah, so in the COMSOL we have the dedicated library. So if you have any kind of the specialty in the material, so we can add into that, and we can see model that the hydrogen diffusion also from the material through the COMSOL. So suppose if in the COMSOL many things or many equation is also not available possible, and you have some source terms because you are in the developing nature, so you want to use source term in your equation. So COMSOL having the capability, you add your equation and as a source terms, or even the in the equation itself. So we have that facility in the COMSOL GUI. So I forgot to share with you, and if you want to, I share with you now. So in the equation, this is sorry, geometry is not important. So in the component, in definition, so one is the variable was there. So you can add your equation over there and give as a source term in the fluid cell. Means you want to use your density or dynamic viscosity. So yeah, the answer is yes. We can model that hydrogen diffusion in the material through the COMSOL.
So the next question is from Mr. Himanshu. What is the solver incorporated in the fuel cell analysis?
Okay, so for solver point of view, so it is just depends on your geometry, which kind of equation you have to solve. If your model is not means very heavy in terms of the simulation, so you can use the normal solver. But in the COMSOL we are using just generally the PARDISO solver, that is called the parallel distributed solver. So we can use the PARDISO in general, but again it depends on your geometry, meshing and equation what you want to solve. So as of now, in the example I showcased to you, we are solving three physics together and do the multi-physics. So with the physics we increase our number of DOF, it is called the degree of freedom. So the solver is depends on the degree of freedom as well. Yeah.
So the next question is, as we know, facing issues with liquid electrolyte batteries, that is safety fire hazards, any risk is possible with fuel cells, cost-wise and performance-wise, which one is better?
So see, as a newer technology, battery and hydrogen fuel cell is also. So we can say hydrogen storage is the bulk, very tricky because hydrogen is a very light gas and it's leak easily. So we have to work on the hydrogen storage. So rest of the part of the fuel cell is not a big deal, because in the fuel cell we just injected as a fuel as a hydrogen, and output we can take the water, so there is no harm to use the fuel cell. But yes, the hydrogen storage is the big tricky. Yeah. Next question please.
So yeah, the next question is, what are the advantages of fuel cells over batteries even in solid state?
Yeah, so same answer for you also. So fuel cell over the battery, again I hope so this is your answer.
So the next question is from Mr. Kar. Give the some ideas about electrochemical synthesis of ammonia generation. I am new in this area.
So for the ammonia generation, the electrochemical synthesis, it is a very vast question. I have to more specific into that. So it is better if you write us on the COMSOL support@comsol.com. So because we need more discussion over there.
So the next question is energy density. Which one is better, battery or fuel cells?
So in terms of the energy density, it is again depends which kind of battery you have, lithium ion, sodium ion, or nowadays SOCl2 battery. So this all depends on the battery, and same thing happen with the fuel cell, which kind of fuel cell you have, PEM fuel cells or some solid oxide fuel cell, nowadays alkaline fuel cells. So it's all depends on the type of the fuel cells and the battery.
So thank you again, Dr. Malviya, for answering those questions and for the great presentation. It was a pleasure to have you with us. So here we come to the end of the webinar. Thank you all for attending and being a lovely audience. We hope you all enjoyed this interactive presentation while carrying back a gamut of information. Hope you all enjoyed this. How So the Volt Post appreciates feedback, so don't forget to share your queries and feedback to us. Thank you so much.
Yeah, thank you so much, Volpost also. So who give me that opportunity to share with my thoughts also. And thank you, COMSOL again, and thank you all of you.